Morning, everybody. As Paolo said, my name is Ashish Mahabal. I work here at the Center for Data-Driven Discovery and with ZTF doing machine learning for them. I'm going to talk about deep learning for classification specifically in both astronomy and a little bit in biomedicine. Excellent introductions were already given to deep learning, so I won't go into the basics of that, but jump into various applications. And I'll point out a few other talks that are happening in the conference in which I'm also involved, but I'll not go into great detail on that. And one of the main things that I'll try to get to at the end is interpretability of deep learning, because say in astronomy, if you do a wrong classification, then you end up wasting a few minutes of a telescope, which is horrible. But if you do that wrongly in case of a cancer patient, either you torture them or put them to death. So you really want these methods to be as interpretable as possibly can be. Starting the stage with astronomy. So what we have is that these are the longer time scales, 1 day, 10 day, 100 day kind of time scales. And those are reasonably well understood. And a lot of science these days is being pushed in surveys going towards the shorter time scales that are here. So there could be transients, for instance, that appear for only a few seconds or a few minutes. So there are FRBs or gravitational wave counterparts and so on. But even in optical, there are short period binaries and so on. So the variability at that area is being pushed. And this diagram was already shown yesterday, that this is the variability tree. But this is really the tip of the iceberg, because the number of types that we have is far bigger than this, and the aim in classification is try to get to each of them. And of course, getting to a big enough data set to be able to classify all of them is not trivial, and that is why what happens is that there are more and more large surveys that are coming up. So CRTS, for instance, has been going on for 15 years, and the time scale is fantastic because you have a uniform system in which you get data. Gaia is fantastic because though the number of epochs is smaller, the astrometry is fantastic, plus we get the data from outside the atmosphere. And ZTF has been doing great as well, though it's only a little over 1 year old. The number of epochs in much of the areas are well over 100 to a few hundred, so the higher cadence there helps. And of course, much of the world is talking about LSST, where we'll, starting from about 2022, we'll have 1,000 epochs over 10 years. But the main thing there will be going down to a much deeper magnitude, 24 magnitude in a single epoch, for instance. And though it will be somewhat sparse, the depth will be giving us lots and lots of objects which we haven't seen before. So all these data can be used for deep learning. Machine learning has been used for a long time, and deep learning, one of the advantages is that you can cut out the intermediate step of features. And so with images, I would quickly point out a couple of things that are going to be talked about. Dima is walking in, and I'm pointing out to something that he will be presenting later about identifying streaking asteroids. So his talk will contain that. And Dhruv has worked on these RoboPol artifacts. There is a poster outside, so be sure to take a look at that. Then another thing that Dima will be talking, he mentioned already in the tutorial yesterday, was BRI, a real bogus classifier for ZTF data, where what we have is a science image, a reference image, and then a subtraction of that giving a difference image. And using these three images, we have this architecture which separates the real and bogus objects. But with deep learning, one can go one step further, and in addition to separating these into real bogus, we can even start with the localization of the object itself. And that is something that we showed earlier with an encoder-decoder network, where what you can do is that you can take a fully convolutional network and give it just these pairs of images, the reference image and the science image, and tell it in the ground truth part where the transient is, and it learns to find the transients on its own. So not only does it give you details about what kind of transient it may be, but even the localization itself. And for that, what we had done is that we had used a lot of CRTS images earlier and trained it with that, mainly with the SN Hunt project in CRTS, where there were many supernovae found by citizen scientists, and then we use varying PSFs to be able to separate these out. And this is how the structure of the encoder-decoder looks. And here you can see the different columns for the reference images, science images, and what current subtractors like Zogi find and what transient it is able to find. And it automatically also is able to get rid of cosmic rays, which are really small and so don't fit in the kind of transients that it has been taught with. And then though it was taught with single transients at a time, it's able to find multiple transients in an image also. And now what we are doing is that we are moving towards applying that to ZTF with the 3K by 3K images and much larger dynamic range and many, many nans, and we want to do that in real time. So there's steady progress that is happening towards that, and hopefully in the next few months we should have that implemented in real time also. A similar encoder-decoder network, and some of the projects that I'll mention are ongoing still. One thing that we are attempting is doing deconvolution with an encoder-decoder network. So if you have an image and if you have its PSF, then in principle you should be able to deconvolve it using that PSF. And we are currently trying out with, say, HST images and ZTF PSFs and also some simulated data. So again, in a similar fashion to the Transinet, what one can do here is that provide it with a training sample where there is a ground truth. With the ground truth, there is a convolved image and the PSF, and so that it will learn how to deconvolve using the PSF given the entire image. But again, what you have to make sure is that these encoder-decoder networks don't come up with artifacts of their own, because if the data, training data are not distributed all over, then the fear is that it'll learn something from your data set and then it'll just conjure those artifacts. We don't want that to happen. So the training has to be intricate. One has to make sure that there are not too many variables, that there is no overlearning that is happening. So all that is going on right now. So the image data, that is what we saw right now, but what is happening in astronomy because of these surveys is that the overwhelming amount of data is in form of time series. There was an excellent introduction to time series yesterday. So with CRTS, for instance, we've got about 500 million light curves over 15 years, and there are several 100 billion, about that number of data points in all. With ZTF, the recent data release, there are more than 1 billion light curves in just over a year. And of course, there will be LSST and SK and so on. So again, in time domain, time series is going to be a big frontier where we need to do more and more. And again, what was pointed out yesterday, that time series in astronomy tend to have huge gaps, they're very irregular, they're heteroscedastic. There are many reasons for that, but we have to live with them, and we have to keep on working with them. And there are many methods which, for instance, ignore errors. Many models do that, and incorporating those is a non-trivial thing. And traditionally, features have been extracted from these, and when you look at all these features, this is how the picture can look. And clearly, all these features are not independent of each other, so even if you derive 100 features, you're not looking at a 100-dimensional space. The inherent dimensionality is much smaller. So what has been done is that you then do, as was mentioned again yesterday, go from this feature vector space, which is very large dimensional, do reduction in the number of dimensions. And finally, in that smaller dimensional space, then you can do your classification. But one method that we introduce is trying to get rid of this feature classification. And in images, it is far straightforward, as we saw earlier, but you can also do that with time series. So what we did, and I'll show that in the next few slides, is that we took a time series and for every pair of points, mapped it to the delta t and to the delta magnitude. And so created a new grid which is very unevenly sampled, almost semi-logarithmically, but with a little bit of domain knowledge going in, so that on the x-axis we have the delta t's, and on the y-axis we have the delta m's. So for every pair of points, a new point is formed that goes in this. So for n points, there are going to be n square points, and you form a density in that. And then these very unevenly sized pixels are then mapped to, or rectangles are mapped to pixels of the same size. So you end up getting an image like this. And look at here, there are only about 30 by 30 bins. So your image is a very small image. And then for each class, you end up getting something that is slightly different. There are more complicating factors, of course. So what happens is that there is the cadence of the survey that comes into the picture. So there is a background that it forms, and you have to remove that. So we used, again, CRTS. There were 7 classes with at least 500 examples from a total data set of about 50,000. And then each class is like a different road here. And then the specifics of a given class are like the moving vehicles here. And that is what you are trying to get to. And the way you get to that is combining all, or putting together all objects of a given class and fitting iteratively a low rank matrix and a sparse matrix to it. So the sparse matrix is what represents the individual object or the individual class, and the low rank matrix is like the background that is formed. And there can be more than one background, of course. One background comes from the survey itself, but another comes from the class, because the class inherently over a long period, given that you are generating n square points from n points, it has this inherent background which you end up removing. And the same method now we are applying to LIGO noise channels. So, and I'm again mentioning this tomorrow or the day after, there'll be a talk by Jess who will go into more details about it. So the motivation there was that LIGO has a very intricate structure, and the coherence is lost now and again, and a lot of time is spent in putting it back. So if we could predict where the coherence is likely to be lost, then what will happen is that we'll be able to put it in mode where we can recover quickly from it. And our initial hypothesis was that it was mainly the ground motion that caused that. So earthquakes is what we started looking at. And there is a lot of data with, so LIGO gets these additional channels, several thousand channels from which you can collect these data. And so we made these similar DMDT plots, and there was a surprise that it wasn't earthquakes, and you can hear more in Jess's talk later. Another thing that we are doing with time series is looking at using RNNs and friends of RNNs. And several months back or a couple of years back, RNNs were thought to be great for, especially variants of those for time series data, going to LSTM, for instance, which has the long short-term memory. So somehow you could keep the short-term memory, but also look at the large-scale time structure in that. But it was soon realized that especially for astronomy kind of data, they're not the perfect ones, because it's not really very good at keeping those things in mind or in memory, which we thought it could. We are trying out some additional variants on that. So Brett Nowell had a paper where he used encoder decoder, and there they were able to bring different lengths of light curves onto the same platform, just like we did with DMDT, and that worked very well. But what we are now investigating is that, again, if you have a cadence of your survey which is very different, are there ways in which you could get rid of some of the points? So some of the experiments that we are doing is where we drop very large DTs. We found that if you have several years of data, and then there are gaps that come because the Earth goes around the Sun, then those gaps can be detrimental. And then there are various ways in which you can give the inputs delta T's rather than T, normalized magnitudes, but in addition you can also give DM. Again, we are not using magnitude errors yet. You can weight your points with magnitude error, but there has to be a better way than that to use that, and we are hoping to find some of that. So for easy classes, we are getting 96% classification results, but not for the difficult ones yet. So that's still out there. In medical science, they are using something different. What they're doing is that there are many observables, but there are also many holes in the data. So for instance, if you have one observation right now, simultaneously you may have another observation, but there would be another times when you don't necessarily have the same observations. So what they're doing is that suppose these two different rows are your observables, and there are certain times like these when both of them are available, and most of the other times one or the other is NA. And then what you can do, rather than taking delta T's of just one of those observables, you can do more complex delta T's coming from both of those. And they have found slightly more success when they use that. And something similar could in principle be used when you have multiple filters. Very rarely do we have simultaneously two filters happening. That will happen if there are observations that can happen with two different telescopes, but more shadowing is likely to happen. For instance, now that TESS is going to start, there are a set of observatories that may be following that, and some techniques like these could be used. So that's something to keep in mind. And certain delta T's being ignored, yes, that can be an interesting thing, because what happens is that suppose you have a supernova, so it has peaked and then it goes flat, and then it stays flat for a long time after that. So the additional delta T's are not really contributing to the science. And if you can figure out for different classes how to take into consideration specific points rather than all the points, in fact, that may improve your signal and it'll improve your classification ability. So that's something that we have been also looking at, and there are again some initial results related to that. So that let me move on to the biomedical part. There are many, many parallels there, two networks that I have been involved with, and this is through my data science work at JPL, Early Detection Research Network, which has several US institutions, and then the flagship program has been going on since 2000, and one of the main emphasis is finding biomarkers there, and the emphasis again is automation, reproducibility, and scalability. And now we are starting to get data sets there where one can use deep learning there as well. So there are some sandboxes that we have set up where different data sets can be brought together, and these are not just imaging data sets, but also data sets say, RNA sequencing data set or other pathology data sets with tissues and so on. So just like in astronomy, there are all these surveys and there is this tree of classification. In cancer, what is happening is that the community is trying to move towards a pre-cancer atlas. So try to see whether cancer can be detected earlier and earlier on. So there are annotated images with nodule census, attendant features, and the annotations are done by trained personnel, but that is where we are also trying to bring in citizen science. So if there is a simple enough architecture and simple enough tutorial, then at least some components can be done by more people. And so again, the same mantra works here, that few labels plus tutorial, but training sample for machine learning, and then when machine learning can take over, much of that can be done by that machine. And so what we have been setting up is in AWS, a big cloud infrastructure where we are using EC2 and Docker images and EFS and then S3 buckets and so on. So for all of these different sets, then we can have these data sets, and different groups are bringing in their data sets, and they have been working in silos so far. So the one main thing that we are doing is trying to see how these data sets can be brought together. And one example that I can mention here is of the lung data set. There's this national lung screening trial. There were 50,000 heavy smokers who were followed over several years, and that's an excellent data set. Not all of them had cancer, but that is how you can get a data set where you have patients with cancer and a control data set where they did not have cancer, but so one can try to separate these things out. And so you have images with benign and malignant types, and then there are of course many sub-features that one has to look at. So there are different kinds of consistency like solid, or there can be part solid, or what is called the ground glass. And then there are different axial levels as well, plus there are pre-cystic or cystic classifications. So astronomy has a handicap, or it has had a handicap for a long time, that all we can do is observe 2D projections of most things, and we cannot experiment with those. And so we have grown used to using those images and do fantastic things with those. But because these people can do experiments, their data sets are far more complex. You can have 3D data sets. In fact, you do have 3D data sets. And then finding out the exact slide in that where there is signal becomes the first problem in itself. And so there are registration issues, there are resolution issues. Traditionally, all the hardware that various hardware suppliers have provided, no metadata comes with that. So the doctors get final reduced products, and that is what you're supposed to use with. So that is where, again, we are trying to go back and trying to see how those metadata could be tied with that to bring those back. And so what happens is that there is a huge workflow that one can build along with it, and that one has to go through in order to not just collect the data, but bring it into a stage where it can be used with our methods. So you start with finding general features, the locations, and then there are some questions that you ask with, and depending on the answer, then there are sub-workflows that happen. And so I have dropped some slides, so this is then the end of the workflow. So you go up to the environment and try to bring those together. So we've been collecting these data sets, and some of the initial results can be seen here with one. So you've got these NLST DICOM slices and segmentation, and there was a Kaggle challenge long back which used a data set on something called Luna 16. So we used one of their data sets and then did both domain adaptation and transfer learning on this data set that we had, and we got an accuracy of 87%. Clearly it has to be much better than that, but this is just a starting stage that we could reach after going through many hurdles of collecting the data in first place. And again, as I said, one of the main things that we'd like to go to is explainability and interpretability of that. So this is the structure of that particular thing that we had. The other thing that we are doing is that now we are putting these things in VR so that the radiologists and doctors can start looking at nodules up close that are very small. They can fly through these things, etc. So there is our abstract has been accepted to SIGGRAPH, which happens in LA this time towards the end of July. And so one of the things that is happening is that the resolution of machines is improving. What that means is that doctors are able to find smaller and smaller nodules, and not all of those are cancerous. But if you find it in your body, then the person tends to think that, oh, statistically I may not be the one, but what should I do? And then when things feed on that fear, then it can go downhill quickly. So we are trying to see how we can try to get away from that. So similar thing happens in, say, breast cancer. These are various structures that are found in breast cancer. And there are these stars which are not very well understood in this, for instance. So sometimes they go away around the time of menopause. There are some of medicines that can get rid of those. But again, their origin is not understood. And by doing early image analysis of that and then feeding it to deep learning, we hope to do more progress. But again, there the workflow is far more complex because there are cases where what happens is that there are interval cancers. So the person has gone to the doctor, there was no cancer, and a year later that person goes again and there was cancer, and you don't know when it came and how fast it can grow. So there are, not only are all cancers different diseases, but even the personalized part comes in. So one cancer can be far faster in one person than in another. So that has to go into all the things that we are doing. This is another example of prostate MRIs, for instance, and so there are many parallels there. So talking about interpretability then, so there is a big program going on in DARPA for the last 2 years, and it is a 4-year program, so it will go on for 2 more years, and David Gunning has been leading that. And then what you have is that you can say based on this thing that yes, this is a cat, but you really cannot say why it is a cat. So this slide says today and tomorrow. This slide is from 2 years ago. That tomorrow has not come yet, and still slowly we are moving in that direction. But what our hope is that we should understand why the classifier says what it says, and that I understand why not, and I know when you will succeed and all those answers. So those are the things that we need to go to. The good thing about deep learning, of course, is that it sits way up here compared when it comes to the power of it, but in explainability, it's way on the left, whereas decision trees, which is the simplest thing, it's very explainable, but it's not very powerful. So what we really want to do is that move in that direction where that arrow is going. And the tools that we currently have, like TensorFlow, for instance, has excellent visualization possibilities. So one can go through those and put a lot of things together, and that starts telling you how your configuration should be, how your network should be, and so on. You can view many options on it, and so on. And so the other thing that is happening is that people are starting to take advantage of adversarial examples. So this, everyone has seen by now that these are 3 images. They get classified correctly, but you add a little bit of something. The images to the eye look the same, but they all get classified as ostriches or something like that, right? And those are being used more and more to that. Another way, what's happening now is that, so traditionally what you do is that you feed images, then change the weights based on your classification. But you can do one more thing. What you can do is that based on the classification you got given your weights, you can also change your input images, and that is what can then lead to something like this, which is the deep dreams area. So that tells you what kind of bias you have in your network, and that is again a crucial thing in order to understand the interpretability. And the same thing then is being used for style transfer, like examples, where you can easily transfer the style of one type onto another type. And then you can form this visualization for interpretability, and there are many areas in which you can do that. So we have got here activation maximization. It sits at the start here and just around the first completely connected layer, or saliency maps, which again start at the start and at the end based on the classes. And then class activation maps, which are near the completely connected layers. And then when we applied this to DMDT, what we found is that rather than seeking out, picking up features in the DMDTs, many of these classes had more information in where there were blank areas. So maybe the ages of how the DMDT were formed. And so that is something that we are looking at more closely to understand why that could be and how we can improve our input DMDTs itself to make our classification rate go higher. These are some saliency maps for different classes, for instance. And now what we are pushing towards is this. So starting from light curves, DMDTs, and so on, go to pix-to-pix conditional generators. So you give it images or DMDTs of one class and try to understand using a pix-to-pix generator what the target should be and what the network is giving us, so that we get a feedback and we can see where. So that could also help us predict when a new observation should be done for a given class. Since my time is up, I'm going to put this summary slide and stop. So astronomy data are great. There are many things that we can do, but much of that is low-hanging fruit, and a lot of data massaging is still required there. But the formulation of the problem is also very important. That's where domain knowledge really comes in, and that's what we are seeing more and more in the biomedical data. So data fusion there again is very critical, and I'll stop with that. Thank you.